Have you ever wondered how AI can spot tumors in a scan or map out blood vessels in a retinal photo? It all starts with medical image segmentation, a process that teaches machines to see the boundaries of structures in medical images. But here's the catch: training these models is tricky. They need tons of data, and different imaging techniques, like X-rays, MRIs, or microscopic slides, can throw them off. Today, we're diving into a study that asks a simple but powerful question: do edges matter? Specifically, can teaching AI to focus on the sharp lines and contrasts in medical images, like the edges of a tumor or a bone, make it better at segmentation? Let's break this down. First, let's talk about what edge enhancement means. Imagine looking at a photo of a tree. Your brain automatically picks out the trunk, branches, and leaves because of the sudden changes in brightness. Those are edges. In medical imaging, edges are equally vital. They help define where a lung ends and the chest wall begins, or where a cancerous mass meets healthy tissue. But here's the thing: most AI models today are trained on raw images without explicitly focusing on these edges. The researchers behind this study wanted to test if pre-training AI models with edge-enhanced data, images where edges are sharpened using algorithms like the Kirsch filter, could improve their performance across different medical imaging types. Think of it like giving the AI a pair of glasses that highlight boundaries, making it easier to learn what's important. Their experiment was pretty clever. They trained two versions of a foundation model, one on regular medical images and another on images where edges were artificially boosted. Then they fine-tuned both models on specific tasks, like segmenting skin lesions from dermatology scans or tumors from MRI images. The results? It was a mixed bag. In some cases, edge-enhanced pre-training led to significant improvements, up to 19% better accuracy in certain tasks. But in others, it actually hurt performance. Why? Because not all medical images are the same. A mammogram's subtle textures might benefit from edges, while a high-contrast X-ray could get confused by over-sharpened lines. This is where the study gets really smart. Instead of a one-size-fits-all approach, the team developed a meta-learning strategy, a way for the AI to decide when edge-enhanced training is useful. They used two simple metrics from the raw image. 1. Standard deviation, how much pixel brightness varies across the image. 2. Entropy, a measure of how complex or information-rich the image is. If an image had high variability and complexity, the AI would opt for the edge-enhanced model. If not, it would stick to the regular version. This adaptive approach boosted overall performance by 16.42% compared to edge-only models, and 19.3% over raw data models. So what does this mean for the future of medical AI? It's a reminder that sometimes less is more. By strategically using edge detection as a tool, not a rule, we can build smarter, more adaptable models. And that's huge, because it means AI could become a more reliable partner in healthcare. Ever wonder how computers can accurately analyze medical images like X-rays, MRIs, or skin scans? Today, we're diving into a fascinating study that's pushing the boundaries of medical image segmentation, essentially teaching AI to see and understand these images better than ever before. Let's start with a big picture. The researchers are tackling a key challenge. Different medical imaging techniques, like X-rays, ultrasounds, or OCT scans, have unique characteristics. What works for one might not work for another. So how do you create a system that adapts to all of them? The answer: a smart meta-classifier that acts like a decision-maker, choosing the best approach for each image type. Here's how it works. The team used a dataset from a major medical imaging competition, splitting it into training and testing sets. But they didn't stop there. They created a subset of the training data that's representative of all imaging types, ensuring their model would be robust. Then they tested two approaches, one using raw data and another with edge-enhanced data, which highlights boundaries in images. Think of it as sharpening the lines to make structures clearer. The models they built: they're based on EfficientVIT-SAM, a powerful architecture known for its speed and accuracy. But here's the clever part. Before training, they used knowledge distillation, a technique where they transferred insights from a smaller, pre-trained model, TinyViT, to their system. This helped the model learn more efficiently, avoiding common pitfalls like overfitting. Now the results. The study found that edge-enhanced pre-training helped some imaging types, like fundus scans or X-rays, but hurt others, like OCT or microscopy. For example, in OCT images, which capture the eye's layers, edge enhancement actually made things worse. But in X-rays, it improved accuracy by over 16%. How did they figure this out? They built a meta-model that analyzes meta-features, like image entropy, a measure of randomness, and standard deviation, how much pixel values vary. These clues help the system decide when edge enhancement would be useful. For instance, in OCT scans, higher entropy meant edge enhancement was less effective. The takeaway: there's no one-size-fits-all solution. By using this adaptive approach, the researchers achieved a 16.4% improvement in cross-modality segmentation compared to models trained on edge-enhanced data alone. For some modalities, like fundus or mammography, the gains were even bigger, up to 163% in some cases. But here's what's really exciting. This isn't just about better accuracy. It's about creating flexible AI systems that can handle the messy, real-world diversity of medical imaging. Imagine a tool that automatically adjusts its strategy based on the type of scan it's analyzing, saving time, reducing errors, and helping doctors make faster, more accurate diagnoses. So what's next? The team suggests exploring different edge filters, like Sobel or PRWIT, and integrating multiple strategies into a single framework. And while this study focused on pre-training, future work could apply these ideas during model fine-tuning too. In the end, this research isn't just about algorithms, it's about making AI a more reliable partner in healthcare. By aligning tools with the unique needs of each imaging modality, we're one step closer to systems that truly understand the complexity of the human body. Ever wonder how doctors spot tiny fractures in X-rays or map out tumors in MRI scans? It's not just magic, it's science, and a lot of it happens in the world of medical image segmentation. Let's break down how researchers are teaching computers to see inside our bodies with incredible precision. Back in the 1980s, scientists were already tinkering with edge detection, like the Sobel operator, a mathematical tool that highlights boundaries in images. Think of it as a digital compass for edges, helping computers distinguish where one structure ends and another begins. But these early methods were like using a magnifying glass in a dark room. They worked for simple shapes, but struggled with the messy, complex world of human anatomy. Fast forward to the 2010s, and deep learning changed the game. Researchers started training neural networks on vast datasets of medical images, letting them learn patterns on their own. One breakthrough: transfer learning, taking a model trained on general images like cats and dogs, and fine-tuning it for medical tasks. It's like teaching a chef to cook sushi after they've mastered pasta. Studies from 2018 and 2020 showed how this approach could spot hip fractures or retinal issues with near-doctor-level accuracy. But here's where it gets really cool. Modern models like SAM and EfficientVIT-SAM don't just detect edges. They can segment any medical image from brain scans to bone X-rays without needing task-specific training. These models act like digital scalpel-wielding detectives, adapting to new data on the fly. And with techniques like self-prompting and efficient distillation, they're getting faster and smarter, even running on a laptop. From the Sobel operator to AI-powered segmentation, the journey shows how far we've come. These tools aren't just improving diagnostics, they're empowering doctors to catch problems earlier, personalize treatments, and save lives. The next time you see a medical scan, remember, behind the scenes, AI is working tirelessly to make sense of the complexity within.